Right. Hello. This is going to be the recording for lecture number 7. Um, Hopefully everything is working. This is, by the way, my second attempt at recording this. I was about like 30 minutes into the recording for lecture 7 with this particular lecture when I realized that I had not shared my screen. So I'm starting all over again. I don't know if you can see the time, but it's very late the previous night. So this is hopefully going to be uploaded within the next hour, with the next couple of hours. And there won't be a lecture today. I'll make an announcement on Canvas. I'd hoped to do this earlier on, but after the snafu, when I was not able to record, I took a little bit of a break and I'm starting again late night. I'll make an announcement saying that there is not going to be an in-person lecture for this week. Rather, this recording will serve as the lecture. There's a couple of things that we're going to cover. We're going to finish what we had left off on Monday, which was the performance metrics, and start linear regression. In fact, we'll complete linear regression today. Regarding the reminders, homework 2, which was posted, it's due this Friday, 2nd of February, and for distance learning students, it is going to be on Monday. The project sign up, please do this by Wednesday evening by 1:31. January 31st. We want to make sure that we know the exact number of teams for us to create those data sets and frameworks for the data sets. Once the teams are finalized, we'll be able to give you the GitHub link for downloading SAM and for downloading the framework that you'll be using to prompt it, and then hopefully to do something on top of it. Right. So with that, let's jump directly into the lecture. What we had stopped, the time at which we stopped on Monday was, I believe we had started looking at precision recall and F1 score. In fact, we had finished talking about precision recall and F1 score, and there were a few things that were still left. The most important of which was the precision recall curve and the ROC curve. In your homework number 2, question number 4 is about these performance metrics. Ideally, the goal was for you to write a function for ROC curve, but since we were not able to do it on Monday, we released the ROC curve code. So if you re-download the notebook, I think it was re-released yesterday, you should have that function within question number 4. So just calling that function, you should get an ROC curve. We'll talk about what exactly that means right now in this lecture. All right. So we had stopped at talking about confusion matrix and multi-class classification. Let's start from there. Just as a reminder, when we talked about accuracy, that is almost the most commonly used metric for comparing between different classifiers, and that's why we have something called performance evaluation. We want to evaluate the performance of given classifiers, right? So let's say we have naive Bayes and we have logistic regression. If someone asks you which is better than the other, then you need a metric, you need a measure to say one is better than the other. Or even between models, let's say naive Bayes, you have used some Gaussian naive Bayes, Gaussian distribution as your, I think we are using GNB, Gaussian naive Bayes, as one of our classifiers. Instead of making the Gaussian assumption, if you're making some other kind of an assumption, let's say Poisson assumption, and you have created a new classifier, now the question is, okay, which is better? Is it a Gaussian naive Bayes or maybe a Poisson distribution one, or a polynomial Gaussian naive Bayes? That kind of questions can be answered by defining some metrics, which are these performance evaluation metrics. Accuracy by itself is insufficient because whenever there's imbalanced data, accuracy is thrown out. The most simplest and trivial classifiers, let's say I have 1 million images that I want to classify, out of which 90,000 images are true and 10,000 are false. 900,000 are true and 100,000 are false. Any trivial classifier that is always going to predict as true is going to give me a 90% accuracy. And just the number 90% makes it sound like that is a very good classifier, but in reality it is not, because in most of the situations it's always classifying as true, and that is not a good classifier. That is not what we want. And that's why we define 4 other metrics, which is the true positives, false negatives, false positives, and true negatives, TP, FN, FP, and TN. So based on that, we also defined precision, recall, and F1 score. We saw this during Monday's lecture. So let's take the same thing, and the visual description of all these metrics is this confusion matrix here. The columns are going to be the actual classes, and the rows are going to be predicted classes. So let's take this example. This is for a multi-class classification, where it's not just a true or false anymore. Rather, there are three classes for us. There are apple, orange, and mango. So let's assume that we have images of apples, oranges, and mangoes. We have used a naive-based classifier to train this model. And our goal is that given a certain fruit, we want to say whether this particular fruit belongs to either the apple class or orange class or a mango class. We have access to its true labels, which is Y labels that we usually see in the classification formula. And we have actual predictions as well from the classifier, which is a naive-based classifier. So in this case, I have access to about 11 Apple images. The way I did it is just by adding up the column here. So let me, this column here is 11. So true class or the true labels for my images is given by the column here in my confusion matrix. So among the 11 apples, my naive-based classifier has correctly classified 7 of them, saying that these 7 images belong to the apple class. And that is the number that you see over here. This is why you have this kind of a confusion matrix. This is what is the definition of a confusion matrix, where the columns belong to the true class of the data points, while the rows are the predicted class. So 7 indicates that these 7 images within my 11 apples have been designated the class of apples. One of them has been designated the class of an orange. That is, my naive base has looked at an apple and thought, okay, this is not an apple, this is an orange, and has classified it as orange. 3 of those images, it has looked at it and classified it as mango. That is essentially what the first column is telling you. You can do the exact same analysis with the second column, which is orange, and you can do the exact same analysis with mango here. Right. So what in this slide, we're just looking at apple. It's just easier for us to understand it. And this also gives you an idea of how we can treat multi-class classification. It's a one versus all strategy. We saw this during SVM as well, where we are considering, in this slide, we are considering apple as our in distribution and orange and mango as our negative class, or it's the all class in a sense. Anything that is false can be either orange or mango, but we really don't care in terms of differentiating it. So let's go back and, based on this confusion matrix, try to get these numbers, which is TP, FN, FP, and TN. On the right top column, top hand, we have the, actually, this should be the opposite. Actual class should be the column, and predicted class should be in the rows. All right. So let's take true positive, for instance. I want to get this number TP. For Apple, hopefully it is very straightforward. Among the 11 Apple images that I have, 7 of them have been classified correctly. So the true positives is 7. So 7 apples have been predicted as 7 by my naive-based classifier. Let's look at the second example, like second metric, which is TN, true negatives. True negatives essentially means that the image that I'm showing to you is not of an apple, and naive-based has correctly said that it is not an apple. Again, I don't care if it is an orange or a mango. I just want to know that it is not an apple. This is the one versus all strategy. So the 4 numbers that correspond to this are in this box. 2 plus 3 plus 2 plus 1. So let's look at the 2 in the middle column here, middle column, middle row. I can't point. So at whenever I'm pointing at a particular number, I'll just either circle it or put a tick mark or something like that, just for you to know. So 2 plus 3 plus 2 plus 1 is the box here that you're looking at as the numbers. I'm discussing the middle row, middle column here, which is this 2. Now this 2 means that the image that you're showing naive base is that of an orange, and naive base has correctly classified it as an orange. Right? So that is the number 2 here. Hence, it is a true negative. It is an orange being classified as an orange. Or in other words, it is not an apple that is being classified as not an apple. Hence, this is a true negative. Same case with 3. It is an image of a mango that is being classified as an orange. Now, it is false. It is not a mango. It is a mango which is being classified as an orange. So naive base is incorrect. But from the perspective of apple, it is a true negative. It is not an apple, and it is being classified as not an apple. Hence, it is a true negative, and I'm adding 3 within my true negative metric. Same thing with the 2 orange mango thing here, as well as 1 and 1. Mango is being classified as a mango. Hence, you have true negative, which is 8. Again, I just want to emphasize, true negative for an apple means that it is classified as not an apple. A not apple is being classified as a not apple. I really don't care about the orange and mango part because I'm looking at it as a 1 versus all. If this apple were orange, for instance, all these numbers would change. And I do think it is a good idea for everyone to go through and make the same analysis for orange and mango as well. So that is about TP and TN for Apple. Let's look at the third metric, which is a false positive. False positive is when the images that you're being shown is not of an apple, but Naive is classifying it as an apple. And that is essentially your row 1, right? When you look at row 1, all the images in row 1 are being classified as apple. 7 of those really are apple, while 8 and 9 that you see here are not apples. Hence, those are false positives. Orange and mangoes are being classified as apples. So 8 plus 9 is 17, which is given by this false positive. False negative, on the other hand, is 1 plus 3. Images that are actually apples are not being classified as apples. So look at 1 and 3 here. The true label for these images are that of apples, but Naive is classifying one of them, which is the one in the middle, as an orange, and 3 of them as mango. So 4 of these images, 4 apple images, are being classified as not apple. Hence, the false negative is 4. Hopefully, this image is giving you a good description of TP, TN, FP, and FN. It's very similar to what we had seen before, except what we had seen before in this table, except that now you need to think of the T and F from a multi-class classification perspective. It's more of a 1 versus all strategy, where the yes and no are, apple and not apple. And sometimes the orange and mango, you don't really need to consider them. And graphically and visually representing it, in this case with columns as being actual classes, while rows are predicted classes. This is what we call as a confusion matrix. Now, there are multiple ways of thinking about confusion matrix. Here, we just looked at a 3x3 framework, right? An MNIST dataset, for instance, it's a 10x10. So 10 actual classes that you'd see in columns versus 10 rows, which are the predicted classes. That same thing, you can analyze it based on the 1 versus all. In this case, we are showing the 5 versus rest, because I guess later on in the slides, we use this example back again. But essentially, given a classifier and MNIST dataset, you're going to be looking at whether my classifier classified 5 correctly. If it did, then those are the true positives. If the incorrect classes, actually I shouldn't say incorrect classes, but not the 5 classes being classified as not 5 are true negatives. In this case, you're going to see 8, 3, 9, 7, 2. All of them are not 5s, and they're classified as not 5s. The false negatives are the 5s, which have not been classified correctly. And false positives are 6, which has been classified as a 5. And sometimes it makes sense, right? Look at this 5, for instance. It is being, I think it's being classified as something like a 6, and it might make sense. Even though it's a 5, the classifier thinks that it's a 6 because there's a small difference here. The line segment that connects the middle portion to the bottom arc of 5, it's almost present. So it might look like a 6. And sometimes it makes sense if you just try to interpret this, right? So false negatives are essentially those 5s that have been incorrectly classified. In this case, maybe as a 6. Now, error analysis in terms of confusion matrix. So if I go up top, the way we analyzed it was based on numbers, 7, 8, 9. But usually whenever we discuss about confusion matrix, it's not a 3x3 matrix. It's usually for a large number of classes. In this case, it's 10, but on ImageNet dataset, for instance, it's a 1000 by 1000 matrix. It's not possible by looking at just the numbers in order to make a decision, but we have to start looking at them as images and pixels, right? So if you look at this pixel, this image here, 0 by 0, this is a number that is being represented as a grayscale image. In fact, this whole 10 by 10 matrix is just a 10 by 10 numbers, 100 numbers that are being represented as this grayscale image. Maybe I'll just very quickly go through what the numbers actually mean. In any grayscale image, 0 intensity represents black, 1 represents white, and anything in, sorry, actually, let me put it in 8-bit integers. So it's 255, 0 to 255, and all numbers within are what we would call grayscale. So in this case, this looks very bright. So I would say this is the number 240, while this is the number 180, 190, and so on. And if I create this number here, this cell, maybe this is like 5, and this is like 20, and this is like 15, right? So it is more closer to 0. It is going to appear black, but the numbers are exactly similar to this. So we're just counting the numbers and putting it over there and normalizing it to make sure it's between 0 and 255. But essentially, we are still looking at it as a set of numbers, but now from a image perspective. So this is what a confusion matrix on the left-hand side is going to look like when we are looking at it as numbers. So row represent actual classes, while I think this is the opposite. The columns represent actual classes while rows represent predicted classes. I'll confirm this again, and maybe I will re-upload the file. So currently the lecture 7 is available under files in Canvas. I may re-upload it by changing this statement over here, because usually, as far as I remember, confusion matrices, the columns are the actual classes while rows represent the predicted classes. All right, so the left-hand side is the normal confusion matrix, but sometimes it's really hard to analyze based on these numbers. So we take the error confusion matrix. So this is the the number of true positives, false positives, those kind of confusion matrices. But maybe we take the inverse. So this is like 255 minus these numbers, right? So in that case, for instance, for those numbers that I just said, this is going to be 15. This is going to be 70, and so on. So we are looking at the opposite direction in terms of what kind of errors are being made by my classifiers. Right. So the means is that, look at this particular thing here. The error for this part is very high. Let's say 255. Again, these are all normalized. So these are not actual numbers, as I mentioned, that normalized between 0 to 255. So this looks like it's 255 at 5 and 3. This tells me, this graph here on the right-hand side tells me that 5 and 3 are the most confusing for naive Bayes. If naive Bayes is the classifier I'm using to create this matrix, 5 and 3 are the most confusing. So in this case, most of the 5s are being classified as, or are being predicted as 3s. Which again kind of makes sense by just looking at the numbers, but error analysis helps us make these kind of analysis essentially that shows us that, okay, 5 and 3 are confusing, and now I can go back and tune my classifier saying that, hey, you have to predict 5 correctly and increase the loss for the number 5 within my training framework, and so on. So that is what essentially this kind of an error analysis helps us in terms of performance metrics. The left-hand side is the actual confusion matrix that we usually use, but on the right-hand side is more of a derivative of this confusion matrix that helps us analyze errors and go back and do some kind of training algorithms on top of it. So that is about error analysis and confusion matrices. So next, let's go to something called precision recall. So precision and recall is something that we saw, which is precision gives a weightage to FP, which is the false positives. So if I look on this side, anything that is a false, if it's being predicted as a true, is considered a false positive. So there is the term FP within precision. But if you look at recall, there is no FP. Rather, what we have is FN. FN, if I come here, a true is being predicted as a false. So let's think of I gave this example in class on Monday as well for recall. Let's think of a medical setting. where the goal is to classify whether, given a certain scan, the goal is to classify whether a disease is either present or absent. Let's say a disease is actually present, which is given by true, but then your classifier mistakenly says it is false. That is catastrophic, right? We don't want that to happen. So recall is an important criteria in the medical domain, but recall is not but FN, which makes recall pertinent, is not present in precision. So you might think that maybe recall is better than precision, or if you're in a different domain for a different application, maybe precision is better than recall. But usually we cannot look at precision and recall by themselves. Rather, we have to look at them as a trade-off perspective. So let's go back to the MNIST dataset. And let's start by looking at just the precision part. So precision is given by TP divided by TP plus, I believe, FP. Let me confirm. Yes, it is FP. So we'll have different thresholds. Just to, okay, so what does threshold usually mean? So when we talked about classification in class, right? So it usually had this kind of a line, and then we had these X's and zeros, and then we decided that you can have three different, you can have a threshold that was here, which, if there's perfectly separable data, you can have this threshold anywhere between the X's and zeros, and you'll be able to differentiate the data. But a more realistic setting is probably when the data is not completely distinguishable and you have some X's and O's in different parts of your data, right? In this setting, now I have multiple choices of where my threshold can be. It can be here, it can be at this spot, or it can be at this spot. So let's consider three such thresholds. And here, and we're showing that essentially here on the axis. Let me put this one. Yes, that's exactly what we are showing here. We're showing it in terms of score, which is in terms of how likely is the given image a 5 or not. Let's start with this threshold here. I'm going to name it as 1 and 1 here as well. So if I'm looking at 1, let me calculate the precision for 1. True positives. So everything on the right-hand side will be predicted as a positive, and everything to the right-hand side that is here is going to be predicted as positive. Everything to the left-hand side is going to be predicted as negative for this threshold, for the number 1 threshold. In this case, there are 3 positives, right? 5, 5, and 5, 1, 2, and 3. There are 3 positives that are true. So its precision is going to be 3 divided by 3 plus. Let's look at false positives. There are no numbers that are incorrectly classified as positive or incorrectly classified as 5. So in fact, this is going to be 3 divided by 3 plus 0, which is 3 by 3, which is 1. That is shown as 100% in this case. Now, let us take threshold number 2. And on threshold number 2, let me erase this. On threshold number 2, what you notice that everything here is classified as 5, and everything to the left of that is classified as not 5. So if I'm looking at that threshold, TP is going to be 1, 2, 3, 4. I'm just counting the number of 5s that are actually classified as 5. So that is going to be 4 divided by 4 plus. I'm going to look at the negative direction. In the negative direction, the number of 5s that have been classified, number of 5s that have been classified as not 5 is 1 and 2. Hence, this is going to be 2. So 4 by 6 is 0.67 or 67%. Hopefully that part is clear. Now, let me erase these things again, and I will start with threshold number 3. In this case, the positives are going to be all these numbers here. The 5s that are classified as 5s are 1, 2, 3, 4, 5, and 6. Right? So it's going to be 6 divided by the 5s that are classified as the negative direction in this particular case. Actually, I think I misspoke here. So I'm sorry. So let me go back to threshold number 2. I think I put in a recall instead of putting in precision at that point. So let me go to threshold number 2 again. So in threshold number 2, my positives were correct. 1, 2, 3, and 4. 4. So my FP, which is false positives, are basically those images that were that are not 5, that have been classified as 5. Which is this number 6 over here. So essentially it's 4 by 4 plus 1, which is 4 by 5, which is 0.8 or 80%. Now the numbers should make sense. So if I'm looking at threshold number 3, the number of true positives are going to be 1, 2, 3, 4, 5, 6, which is 6 divided by the number of false positives are going to be 1, 2, that's it. So it's going to be 6 divided by 6 plus 2, which is going to be 0.75, which is given by 75% over here, right? So if you look at precision, threshold number 3 was given by 75%, threshold number 2 gives me 80%, and threshold number 1 gives me 100%. So if the goal is to maximize the precision, then it's very simple. I'm always going to choose threshold number 1, which is always going to give me 100% precision, right? But it may not be the best threshold, best classifier. The reason being that you're taking the least risky approach. All the 5s in this case are classified as 5s, but maybe there are some difficult 5s that are not being classified correctly, which you want it to happen. You want this 5 to be classified as a 5, which you're never going to get if you use this particular threshold, right? So this is when it's not very easy to say that one classifier, that one threshold is better than the other based on the precision. And that's why you need to now look at the recall as well. So let me delete all these things at this point. So 3 plus 0. All right, so let's go back to now. Actually, let's look at the thresholds from the left-hand side. So let's look at threshold number 3 to start off with. So the way recall is done is, let me make sure, F divided by Fn. Yes. So recall is given by TP divided by TP plus Fn. So true positives divided by true positives plus false negatives. Right? So let's look at threshold number 3. In this case, the true positives are given by all these numbers here where there are true positives. So 1, 2, 3, 4, 5, and 6. So for recall, the true positives is 6 divided by 6 plus false negatives. So how many not 5s are classified as 5s in this case, right? So you see that there is no 5s in this negative predictions at all. So this here is 6 divided by 6 plus 0, which equals 1, which is shown as 100% in this particular case. Right? We're just calculating the Fn in this for this threshold. That's it. Now, if I were to do the exact same thing for the second threshold, which is here, so this will be the positive predictions and the left-hand side will be the negative predictions. And I'm going to look at the positive predictions for the number of true cases, 1, 2, 3, 4. So there are 4 true positives. And I'm going to look on the left-hand side on the negative predictions for the false cases. So in this case, there are 1 and 2. There are 2 5s in my negative prediction, right? So those are false negatives. So it's 4 divided by 4 plus 2, which is 4 by 6, which is giving me a 0.67 in this case. I can do the exact same analysis for this threshold 1. So let me delete this, and this. All right, so in this case, I'm going to look at the true positives on the right-hand side of threshold 1, which is 3 divided by 3 plus, and I'm going to look at all the negatives. So in all my negative predictions, how many are actually incorrect? How many are 5? 1, 2, 3, right? So this is 3. 3 divided by 3 plus 3, which is half, 0.5, which is given by my 50%. So an important thing here to see is that based on the threshold, I have opposite characteristics. My precision, 75, it's increasing from 75 to 80 to 100, while my recall is decreasing from 100 to 67 to 50. So this is this is why we have this idea of precision recall trade-off. If one increases, the other decreases. And this is like a graphical representation. We just saw 3 thresholds, but maybe if we had, in this case, how many are there? 1.2 million thresholds. This is how the results would look like. Your precision, your recall would start very high and decrease while your precision is going to increase. And it makes sense, right? The least risky way, which is a very high threshold, is going to give you a very high true positives, no true negatives, and hence you will have a very high precision, which you see over here. I hope this part is clear. How we got from this to the graph here. All we are doing is putting the threshold on the x-axis. Instead of just showing it on this graph, we are showing it on x-axis over here. And y-axis is a combination of 2 things, which is the precision and recall. Based on this, we are going to construct a graph. Instead of having threshold on the x-axis, we will have recall on the x-axis, and we are going to have precision on the y-axis. This is what we call a precision recall curve. And hopefully this part is clear. So let me go here in this and create a few, maybe I'll use blue here. Let me say that this threshold, this point is number 1. Your green, which is recall, is very high, while precision is very low, right? So if I want to represent point number 1, maybe it's somewhere here. Your recall is very high and your precision is low. If I want to have another point, let's say at this stage, points again are based on the x-axis over here. So in this case, my precision is around 0.6, while my recall is around 0.9, I would say. So that would be somewhere here. So I'm going to name this as point number 2 and here. So let me create another point, yellow, which is going to be somewhere here and here. So at this stage, my recall is around 0.45, while my precision is around 0.95. So that is going to be somewhere here. So this is point number 3. What I'm trying to say here is that given this threshold on the x-axis and plotting precision and recall, we can take the points from this graph and convert it into this idea of a precision recall curve. The advantage of doing something like this is it helps us make this nice statement, which is precision starts to fall sharply at around 80% recall. So at around 80% recall, precision starts to fall sharply. What that means is that if we were to construct some kind of a model here, right? Like a tangent model here, the slope of that model, if it's a linear one, is going to be very high. The slope here is going to be, let's say, minus 0.7 versus, actually it's not 0.7, minus 7 is probably a more accurate slope here, while here it's like minus 0.3 is the slope. So precision starts to fall sharply around 80% recall. Maybe you have a different kind of a classifier. This was a naive-based classifier, let's say. Maybe you have a different kind of a classifier that fell at recall 90%. That was like this, for instance. And in that case, I could say that even with a very high recall, I would have a high precision. So I would say that this logistic regression graph is maybe better than the naive-based classifier. This is a way that you can compare between, again, the goal is performance evaluation, and we are trying to compare between different classification algorithms. And this is one way of saying that, let's say, LR is better than naive-based. So this is based on precision and recall. A very similar idea is there in ROC as well, except in this case, we are not looking at precision versus recall, but something else called the true positive rate and the false positive rate. I don't know if I explained it here, but essentially when we were looking at this error curve, we are looking at the positive rates. So we are looking at the number of, we are counting, I need to make it in yellow. We are counting the number of values over here and then dividing, if this was, let's say 10, and then we are dividing by the total number of elements within that column. Let's say there were 10,000 and assigning it that value. So it's the rate, the total number of actual images there are within that class divided by the number of elements that has been either classified as class 0 or class 1 and so on. So rate is essentially a normalization part, and usually this is used in more medical domains. We don't call it sensitivity or specificity. We don't call it sensitivity, precision or recall. We call it sensitivity and specificity. Sensitivity is the same as recall. Specificity is a little bit different. It's not the same as precision. It's Tn divided by Fp plus Tn. So it's widely used in medicine. Sensitivity is the ability of a test to correctly identify patients with a disease. Again, Fn, very important for in a medical setting. That's why we have sensitivity that has access to Fn, which is the same as recall. Specificity is the ability of a test to correctly identify people without the disease. Both of them are very important in medical setting, and that's why we have these ROC curves that exists with y-axis being TPR, which is the true positive rate, and the x-axis having FPR, which is the false positive rate. Exact same analysis that we did for precision recall works for true positive rate and false positive rates as well. Based on different thresholds, we can calculate this ROC curve. The difference between the two is the characteristic. Look at the precision recall trade-off. Here, ideally, with high, maybe I won't do it here, but if this is precision recall, this is usually how a precision recall graph is going to look like. At least for a good classifier, for a high precision, you'll have a low recall. And hopefully, even at this stage, where your precision is quite high, 0.8, your recall is also quite high, 0.6. So you want your classifier, precision recall curve, to be as similar to this dotted line as possible. This dotted line, this is like the best possible classifier, right? ROC curve, on the other hand, with true positive and false positive, is the opposite. You want it to have a high slope in the beginning portion compared to before. In this case, maybe m is 7 versus m at this stage is 0.3. Right? We had the opposite here. This is -7 and -0.3. Here 7 and 0.3. So this is the difference between ROC and precision recall curve. So for every classifier, we can have this kind of a graph between the ROC curve or the precision recall curve, but it's not always possible to always draw these curves. And better idea is to have some quantitative metric under them, and that is given by your your AUC, which is area under the curve. So if I go back to this, all I need to do is literally calculate the area under this curve. So, you can estimate this in multiple ways. You can say that this is a bunch of like rectangles that are connected with each other, and you can take that as one of your as calculating the area. I believe the way scikit-learn does this, there are functions for creating this. The way scikit-learn does this is that exact thing. It's gonna create like small rectangles and take the area of each of these rectangles. It's gonna add that and give you the area under this curve. Right? So that is like a quantitative metric. So let's analyze what that area means. Let's say I have my data where the positives and negatives are completely separable. So it's separable in this case, right? So I can create a classifier. My ideal classifier is going to be somewhere in the middle. I can have a 100% positive and 100% negative. So I don't have to, there's no trade-off in this case. With a very high sensitivity, I can have a very high specificity, or I can have a very low 1- specificity. So in this case, you have the ideal graph, which is given in the green here, and your AUC is going to be 100%. Let's look at the third graph, which is essentially your data is non-separable. The negatives and positives are overlapping each other. What happens in this case is it doesn't matter the threshold you're choosing. It doesn't matter what kind of classifier you're choosing. You'll not get a very good ROC curve. It is going to be a chance. It's just 50%. It's a random kind of a classifier. It doesn't matter if it's here, 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 here. Any of these thresholds is going to give you 50%, right? The reason being that if I go back to this curve here, let me just first delete all these things. So when your data is completely non-separable, what is essentially happening is that you're taking this particular point over here. It doesn't matter what threshold you're choosing, your precision recall is not changing. It is going to be something like this, maybe something like this. It doesn't matter what it is, right? The numbers don't matter. It's just that it is not changing. It is going to remain exactly the same thing across different thresholds. So in that case, threshold doesn't matter, and you have this kind of across at 50% accuracy. Not accuracy, sorry, area under the curve. More realistic scenario is the second one. Your data is not completely separable, so you would have to choose some threshold, which is either this or the second one that I'm drawing, or the third one that I'm drawing. And across this, now you can say that, okay, one is better than the other based on the threshold that you've chosen. Again, remember, each point here is a threshold similar to what we had. I showed it for precision recall, but the same thing exists. Each point here, 2, 1, 3, was a threshold that you can choose. So in this case, you can basically say that given this kind of a classifier, there is one threshold that I want my application to have based on the true positive rate and the false positive rate. This AUC is more across thresholds. That is, given a logistic regression classifier, it doesn't matter what threshold I'm using. If this was naive Bayes, maybe there is a logistic regression classifier that was something like this. And this is LR, and the AUC for that would be greater, right? So you can compare. Again, the goal is performance evaluation across different algorithms and different classifiers, and you can compare based on this. Sometimes, again, this in imbalance classes, AUC for ROC may not be the best idea, because remember what ROC is doing. It's doing across TPR and FPR. In imbalance data, it is easy to confuse the true positive rates. It can be extremely high for imbalance data. Hence, you can have a very large slope for between the TPR and FPR, and you can have a very good accuracy. Sorry, again, I keep saying, I see A and I think accuracy, but no, AUC is the area under the curve. It's 0.92 for this particular classifier. For the same classifier, my precision recall, if I plotted this, as you can see, it is almost similar to 50%, almost similar to chance thing here, right? So this AUC in this case is 0.6 maybe. I'm just making this, it's an example number, but it's 0.6. So if under imbalance data, your ROC might appear very high, in this case 0.92, but your AUC for your precision recall curve is going to be low, 0.6. So when there is imbalance data, it's better to see the precision recall curve and the area under it rather than the ROC curve. Again, this is for negative, positive, plus 0.95. Usually I say the opposite, 900,000 positive and 100,000 negative, but it could be the opposite as well. Imbalance data doesn't necessarily have to favor the true class. Rather, it can favor the negative class as well. All right, so this, what we have here is, let me go to the next one. All right, so what we just saw was classification performance metrics. And this ends the first part of the course, which is going to be about classification. The next part is going to be about regression. If you see in the course content, ideally, slide 13 is where we should have finished on Monday. One of the reasons I'm doing this, recording this video lecture is we want to make sure that that still continues. Because ideally, by the end of February, we want to finish regression, want to finish clustering, and move on to deep learning, neural networks. So Also, this is there for the homework as well, so it's very important that it's there within the recorded lectures. So if we cannot finish tomorrow within 1 hour 15 minutes, that's why maybe this lecture will take more than that amount, maybe about 15-20 minutes. I'm not sure. By the end we'll know how much it is going to be. Now, regression, it's in lecture number 3, we looked at logistic regression, which is, and even though it is logistic regression, we looked at it from a classification perspective. And that's not always a good way of doing it. There were multiple places in lectures 3 and 4 where I wanted to talk about something, but I was not able to because we didn't have the requisite math. We were not looking at it from a regression perspective, but we were looking at it as a classification perspective. For instance, regularization. Whenever we showed the table, in the summary table between, let's say, naive Bayes versus logistic regression versus neural networks versus SVMs, the final column was something called overfitting. But I don't think I have explained what that means, overfitting, at all across the last 6 lectures. The reason being that it makes more sense to talk about regularization and overfitting in a regression setting than it does in a classification setting. So we'll revisit a few concepts that we have talked about in classification, but from a more mathematical perspective and from a more systematic perspective, I would say, rather than mathematical, in regression. In fact, in many machine learning courses, we start off with regression as a first topic rather than classification. But the problem then, and not the problem, but the difference then would be that the first couple of homeworks would be more mathematical. It would be more problem sets rather than introducing machine learning from a coding perspective. It would have introduced from a mathematical perspective. So we tried to change that. So we started with classification to get you familiarized with scikit-learn and all the libraries that exist. And then we'll be doing regression in this case now. All right, so with that, what exactly is regression? So the difference, maybe it's best explained by talking about the definition of regression is best explained by talking about it from the perspective of what is different between classification and regression. In classification, we had output variables y that were categorical. In other words, my y could either be class 1, class 2, or class 10, or it could be a cat, dog, horse, bird, or all these things, right? It had a finite number of elements. Y could be between 1 to 50,000 or 1 to a million, but it was still finite. It was a discrete set of outputs that we could get. The difference in regression is that Y is a continuous variable. The goal in classification was, given a certain data point, we want to classify that data point between n finite classes. In regression, given n data points, we need to construct a model. We need to construct a model F that finds the relationship between X and some continuous output variable Y. So usually classification is talked about in an inference setting, while regression is talked about in a training setting. So we have access to a large number of data points here. So let's look at this example, for instance. Let's say y-axis is the amount of sales of umbrellas, while x-axis is the total rainfall. It's quite clear to see that as the amount of rainfall increases, the amount of sales for my umbrellas also increases, right? And maybe there is a very simple relationship between them. If I plot a line, you'll see that it's almost a linear relationship. And this linear relationship is given by 20 plus 0.4x. That is, with an increase in rainfall, there is an increase of amount of sales of my umbrella as well. And each point maybe is basically on a given day, the total amount of rainfall. So I guess there are about 100 to 200 points in this case. And we are creating a relationship between the amount of sales on those 100 to 200 days to the amount of rainfall on those 100 to 200 days. So this is a linear relationship within regression, but the goal again is we're talking about a regression here, and instead of looking at it from an inferential point of view, where we are looking at a class of a given data point x, we are saying that in regression, given n data points x, we are finding a model that best fits all the n data points given a certain continuous output variable, which is y. Now this example was for a linear relationship, but maybe that's not the case. Maybe there's other kinds of relationships that is possible. In this case, this is with a positive slope y. Think of this as y equals mx plus c. Maybe there can be a different example where we have y equals minus mx plus c. And there's a non-linear relationship, which is theta naught plus theta 1x plus theta 2x squared. Right? Because this is as you can see, it's more of a polynomial parabolic kind of a function. So there's a non-linear relationship. Actually, if let's compare this to how we were thinking about it from a classifier perspective, because there is a slight difference between the two things, but it's very important to understand this difference. In classification, the non-linearity was with respect to this decision boundary. We used to call this as a decision boundary that is non-linear. So it is represented by a function that is given by theta naught plus theta 1x plus theta 2x square, and we could get this decision boundary. In regression, it's not a decision boundary. Rather, it's just a simple relationship given some data points and y. In lecture number 3, if you remember, I think I spent quite a bit of time in order to take x1, x2, x3 data points, convert them into x1, y1, x2, y1, x3, y1, and so on. I used to convert them into this so that I could plot it in this kind of a graph. So I could plot all these three as circles like this. And if I had x4, y2, x5, y2, and x6, y2, I would plot it like this and then say that there is some decision boundary that separates them. The goal here is that it's not this kind of in fact, this idea of x1, y1, x2, y2 is built into the framework itself. Every single point has x and y associated with it in regression. Same thing in classification as well, but we were not able to express it. It's not as intuitive to express it in terms of a graph as it is in regression. We'll talk more about this in a little bit. In fact, in this lecture, we'll discuss linear regression and a more generalized version of that linear regression and how to basically find the best possible model. Right? So in this case, this is one model. Maybe there is another model that looks like this. Maybe there is another model that looks like this. Which is the best model is something that we need to decide. And that is an analysis that we are going to do. All right, so let's come to linear regression. This is another example for linear regression. This is life satisfaction on y-axis with GDP per capita. I'm not really sure which year this is from, but essentially, given different countries' GDP per capita, we can we get data for the life satisfaction index as well. And if you plot it, just these two things, then you have this kind of a linear relationship between GDP per capita and life satisfaction. So, you can say this line, we observe a trend that life satisfaction index increases linearly as GDP per capita increases. This is based on the fact that there is a linear regression that is possible. So when my samples are one-dimensional, that is, I have only a single feature here, right? If I go back to the table, the only feature I have is GDP per capita, and output is life satisfaction index. So given a single feature, one-dimensional feature, there's a single line that is going to give me the best possible model. And this model is characterized, since it's a line, this model is characterized by theta naught and theta 1. We'll use these as our intercept theta naught instead of using mx plus c, where c was theta naught and m was the slope. We'll use theta naught and theta 1. Intercept, we'll be calling it a bias. Again, this is similar to classification. Bias is theta naught, and our slope in this case, which was weights before, will be theta 1. They serve the same purpose. Essentially, my bias is given this data points. What is the best intercept of the best line that moves it away? So for instance, this is the intercept here. So this theta naught is given by this intercept for this blue line versus theta 1 is some slope, something here. In fact, in the next slide, I think I have the results. But essentially, y equals mx plus c is the same as life satisfaction equals theta naught plus theta 1 into GDP per capita, which is my feature in this case. So the goal of today is, in fact, to try to find theta naught, theta 1. Since this is just an example, let's just say I'm giving you the answer here. Theta naught is 4.85, which makes sense, right? So if you looked at this one, in fact, if you just look at this, the best theta naught, the intercept from 0 is given by 4.85, and theta 1 is 5 into 10 power minus 5, or as close to 5 into 10 power minus 5 as possible. So I can take a linear line and fit it for this particular problem, for the life satisfaction and GDP per capita. Again, this is just an example. We're not trying to differentiate or classify between countries in this case. We're just trying to, given life satisfaction and GDP per capita, we're trying to find a relationship between them. And that is essentially everything that a regression does. Given a certain amount of data points, it gives you a function between the given data points and their outputs. So let's take that same example and now generalize it across different points. So this is exactly what I was showing before, which is every data point is two things right now, and we call this an ordered pair. We have x1, y1 until xn, yn, where all these input samples and output for those particular samples can be represented in one bracket over here. This is x1, y1, and this nth data point has y of n. Again, if this were classification, the number of y's is probably going to be more limited than the number of x's. You'll have a number of different data points, all of which are present in the same class. Usually in regression, it is not that way. There's, given a certain data point, it will have its own output y, because think of it from a graph perspective. All right, so given a data set of n samples, where each sample is this x1, y1 to xn, yn, each x can have p number of features. So that's still the case. So before we had just one feature. In Iris data set, we have 4 features, so on. So it can still have 4 features. Your yi is a scalar output, and linear regression makes a certain assumption between the relationship between x and y, which is that they are linear. So that means that my theta, which is given by p, theta 1 to theta p, models yi based on this equation. Yi is given by theta naught plus theta 1 xi1 until theta p xi of p. Again, the same simple equation holds, which is y equals theta naught plus theta transpose into xi. Hopefully this hyperplane image is familiar, which is given 3 dimensions. So I have, let's say, 2 features to start with, x1 and y1. I'm representing it as orthogonal basis functions over here. Theta 1 and theta 2 are essentially giving me this plane, which is the slope for this, this plane, and theta naught is the intercept across the y, across the 0, 0 point. Again, this is 2 features, which is x1, x2, but then it has a y value associated with it as well. And in lecture 3, this is what I was talking about. Like even a single dimensional thing, you'll have, you need to convert it into 2 dimensions. So if it's a p-dimensional vector, you need to convert it into a p plus 1 dimensional vector, so that you will have access to the theta naught and y as the 3rd dimension of the p plus 1th dimension. All right. So we have y is equal to theta naught plus theta transpose x as our linear regression model. But generally, this is not preferred. We want a more compact representation as y equals x theta. The reason is in the next slide, because I'll come back to the previous slide in a little bit. But the reason why we don't want y is equal to theta naught plus theta transpose x is because whenever in regression, whenever we see this form where a scalar, where a single number is adding to the dependent variable, which is x, we think of that as a residual error. We don't think of it as a bias. We consider that to be something error. So maybe graphically we can show this. So if I were, let me take the best example. Okay, in this particular case, right, y equals mx plus c is not modeling every single data point. The model is not like this, right? This would be a very bad model. where it's connecting every point. Rather, it's taking like the average of all of them and creating the best fit function. So what happens is that in each of these cases, there is an error associated with each of these points, both in the positive and negative direction. So there is some kind of an error usually that is associated with this. And we'll talk about this later, but in machine learning, this error is kind of required. We don't want our model to overfit. In fact, the other thing that I showed before, my FFX model was overfitting to each of the data points, which we don't want. We want a machine learning model to learn. So given a new data point, X, it should still be able to model it correctly. If it had that kind of a weird shape where it was connecting every single point, it is definitely going to miss this, because all it has done is memorized where the data points were rather than learning the relationship between the data points and Y, right? So we usually think of linear regression not just as Y equals theta naught plus theta transpose X, but rather as Y equals with some residual error that can exist. And this residual error is represented as epsilon. The point I was trying to make before is that we don't want theta naught to be explicitly written in this way. Rather, we want to find a way where we'll have Y is equal to theta transpose X, where this theta is actually a combination of theta naught and all the other thetas, theta 1 to theta p we had before, right? And this is something that we saw in homework number 2. In fact, there was a Piazza question on this as well, but I don't think I was able to explain this properly then, because we still had not looked at regression. From a classification setting, it doesn't make too much sense. W transpose X plus B, you don't want any kind of an error. This for a linear classifier, it should just be a linear W transpose X plus B. But when it comes to regression, we want an error term, and we don't want to confuse bias with error. So what we do is we try to incorporate this theta naught within theta itself. And the way we do that is by creating this trick. So we take X, which is our data points, and we concatenate the 1 to it. So in this case, let me just say that I have my X, and then I concatenate a number of ones based on the dimensionality of X. And then when I create my theta or my W weight function, it's going to be theta naught and theta 1 is to P. This is X1 is to P, by the way. So when you look at this as a matrix multiplication, theta naught multiplies with 1. So it's theta naught plus theta transpose or X transpose P. Actually, in this case, I think I've written it as X transpose into theta. Right? So what I'm doing is concatenating X with ones, so that when I construct my theta, it has an inbuilt theta naught associated with it. So just by saying Y equals X theta, I am now able to model both theta naught and theta 1 to theta P within this framework. Again, my entire goal is that I want to create this kind of a succinct representation over here. In classification also, this I said that W transpose X plus B makes sense, but in classification, we do this because we want to make sure that we don't have bias within the optimization setting. We don't want to, you'll have two different equations. You need to create a gradient for both W and B. Instead of that, if you can have this single representation for theta, where it's B and theta 1 to P is there, you can basically optimize just a single function, which is theta, and you'll be able to get your result. So this is why we did this in homework number 2. Specifically for regression, we want to make sure that epsilon term is given its space in order to represent it correctly. So our generalized regression model hence is going to be X of theta cap plus epsilon, where theta cap actually consists of both the theta naught cap and theta 1 to theta P, which we have over here, and X is a concatenation of Y to xn1 to xnp. In fact, in homework number 2, if you look at the place where we have defined the class itself, you'll see that the concatenation is done in, I think, the first function itself when we have defined our logistic regression. So based on first concatenating it, then we create our theta function. We called it W in homework number 2, with the same size as X. So the 1 is in fact part of the created W in homework number 2. All right. So this is the general form of y equals x theta cap plus epsilon, where epsilon is some residue for our function. The goal for us for the rest of this lecture is to find the best possible theta cap. In other words, I want to find the optimal theta cap that is going to give me the best relationship between y and x. Right. One more thing, which is the dimensionality of epsilon is going to be epsilon 1 to epsilon n. So that means that every single data point has some error associated with it. And so if I were to go back to this slide, I'm not sure where I had it. Yes, here. This is epsilon 1. This is epsilon 2. Epsilon 3, and so on. And for n data points, there's going to be some error that is associated with it. Hopefully, the definition of epsilon is clear. It is some residual error given a theta cap, and the goal is to have the best possible theta cap to have the least possible epsilon. Now, let's try to go about in a systematic way, trying to find the best possible theta cap. The next few slides are going to be math heavy. I'll try to first talk about the motivation for each slide before going into the math part itself. So in this case, we are trying to find the best cost function, right? This is very similar to what we did in classification. To find the best theta, we need to use some kind of an algorithm in order to create the best possible theta, WB before. And to do that, we need to have some kind of a loss function, some kind of an error function. So we start with that. We want to create, and the error function we'll be using is this least squares cost function. And to do this, we'll start off with epsilon. So epsilon, again, is the error between the predicted value versus the true value. We'll make some assumptions about this epsilon. One, which is that it is IID. It is independent and identically distributed. IID is something that we'll be using now, but I'll explain more when we come to the later part of the course. Again, there's many things that is going to make sense throughout the length of the course rather than at every single point. IID essentially means that I'm going to pick a point and I'm going to pick a next point, but I don't care about the previous point when I'm picking the next point. That is essentially what IID, independent and identically distributed, is telling me. Next, I'm making an assumption about epsilon. Here, epsilon is given by a Gaussian distribution. I'm just going to say that all my error functions. So if I were to go back here, all these errors, if I were to plot them, let's say error was 0.2, this is 0.3, this is 0.1. So if I were to plot everything, it would probably be 0, and this is maybe 0 was incorrect here. I'm essentially saying that it's some distribution here. Maybe 0.3 is the mean distribution, and everything else is like 0.4, 0.5. This is 0.2, 0.1. So most of epsilon is around this range. And we are assuming that if you create a distribution out of it, epsilon has this kind of a normal distribution associated with it. Let me go back to where I was. All right. So that means that if I have a PDF, a probability distribution function over epsilon, hopefully this equation should be straightforward. This is essentially a normal distribution. Now, what this implies is that y equals x theta cap plus epsilon. Epsilon is a random variable with Gaussian distribution. Since this is a random variable, any function of a random variable, which in this case is y, is also going to be a random variable, right? So p of yi given xi, given some theta cap, which is our posterior, which we had seen in lecture number 3, is also has some kind of a probability distribution function. So yi is Gaussian distributed based on this equation over here. So epsilon I is yi minus theta cap transpose xi. This is because epsilon is equal to y minus yi, or y minus this one here. Epsilon equals y minus x theta cap. That's all that is being put over here. In many cases, I'm seeing that theta cap, theta transpose xi is in the opposite region, while here it's x theta cap. So if I go back here, the way we have defined it is x1 transpose, x2 transpose, xn transpose is x, right? So you can think of it as x transpose theta cap. And when there's an A transpose B whole transpose, it's usually given B transpose A. Simple linear algebra. So whenever we had W transpose X plus B, just think of it as we're just taking a transpose here. So that's going to be X transpose of W, and X transpose we are defining to be capital X. So I'm trying to say that X theta, this is the same as theta transpose Xi over here. So, you shouldn't be confused when you see capital X theta cap and theta cap transpose small Xi over here. All right. So given this posterior, this is where we are going to start finding our loss function. So so this is for a single data point, xi comma yi, right? So for the entire data set, we want y given capital X, and let's call that loss function as L. Not loss for sorry, the likelihood function as L theta cap X comma y. We already know that this y given X for some theta cap is going to be a probability function, and it's going to be IID based on the fact that epsilon is also IID. And I'm going to use my same methodology. Since it's IID, what that means again is that given my present sample, it's completely independent of the previous sample. So we can now use the same assumption that we did with naive Bayes, where each of the samples, P of xi, yi given xi, are independent from each other. So I can use it. So instead of having P of x1, x2, x3 until xn, given some, or in this case, I think it's y1, y2, y3, yn, given some x, I'm now taking this P of y1 given x multiplied by P of y2 given x, and so on. That is essentially what this statement is telling you. Since all my data points are independent, which is given by my IID, I can take it as just a multiplication. A joint distribution now becomes just a multiplication of all independent distributions. We already know P of yi given xi is given by our Gaussian distribution. We have seen that in the previous slide. And going through it, whenever we have a pi, we usually want to take the log function because it's more difficult to have multiplications. Rather, we would prefer to have additions. So the pi becomes sigma. There's going to be a log function, which is going to reduce to this particular value. So log likelihood, this is the log likelihood, is given by n log 1 by root of 2 pi sigma minus 1 by 2 sigma square summation 1 to capital N y minus theta transpose xi whole square, right? Again, just what we had established regarding the likelihood function and xi yi is now being we now have that as part of our log likelihood function. That's it. Previously, we had it for a single data point in the last slide. In this slide, we have it across the entire data set. So look at this expression on the right-hand side. Our goal is to have a high likelihood, right? So we want to maximize our likelihood. And in the homework, you have seen that what we call that is a maximum likelihood estimate, or MLE. And the way to do that is by maximizing this equation on the right-hand side. So either I can maximize n log 1 by root of 2 pi sigma, or I can minimize 1 by 2 sigma square yi sigma yi minus theta cap transpose xi whole square, right? Either I can maximize this expression or I can minimize this expression. The reason is that this is a positive value and this is a negative value. But the problem is there's no way I can maximize n log 1 by root of 2 pi sigma. The reason being that all of them are constants. Now, and this is where usually we talk about how big data is good for machine learning, because bigger capital N is, the better your algorithm is going to be. Even intuitively, that makes sense. The more training data you have, the better your algorithm is going to learn from it, right? So when you maximize capital N, you are maximizing this terminology. But generally, we think of capital N as something that is constant. That is, once I'm given the training data set, I cannot ask for more training data. That is something that I need to work with. So in that case, what I need to do is minimize this on the right-hand side. we minimize the negative log likelihood. Look at this. So it's minus log L of theta cap xy, which is equivalent to this expression. We saw this exact same thing in lecture 3 as well, except there I tried to motivate it based on the shape of the curve. It is true for classification, this is completely true, but it's not as intuitive. Hopefully by looking at this math, it has become more intuitive what negative log likelihood is. Based on this and based on binary, like a softmax probability that we saw for neural networks, we have a cross entropy loss that is on top of this. So everything that we are doing in cross entropy loss and negative log likelihood is trying to minimize this expression. Hopefully this part is clear. So what this means is that I have something called a least square cost function, which is given by this, right? So the negative log likelihood, which is minus log L theta cap x comma y, is our cost function, which is the distance between estimated y cap and target y. So our error function, it's not just a simple subtraction between y cap y, but rather it is this negative log likelihood. Given in a maximum likelihood estimate setting, we have access to this least square cost function, which is L theta cap 1 by n y cap minus yi whole square. And hopefully this example here gives you the difference between what those distances actually mean. A simple yi minus yi cap is just this kind of a just addition of all these error bars. But when we look at it from least squares error, we are also looking at the area, in fact, between these values. So the least squares error can be thought of as the total area of the blue squares rather than just a simple measure here. Again, the reason we do this is that once during test time, let's say we get a new error, new data point, which is like this, it's already something that is included within the training data set, right? Because you've calculated that error within the training data set by choosing this nice loss function, least squares error, which is already considered this red point within the training distribution. So the error is something that it has already seen before, and it will be able to make a good decision based on a new data point that has now come in during inference. So that's why sometimes that again, this is just one distance, by the way. There's many other distances that we can use, but least squares is probably the most used and the most well analyzed loss function there is. All right, so we went through this exact process in lecture number 3 as well. So our goal was to get the most optimal set of theta parameters. To do that, we defined a cost function called negative log likelihood. Now that we have defined negative log likelihood, the goal is now to go back and say what the optimal parameters, which is theta cap star is going to be. To do that, we need to create this loss function, and we need to have the least possible loss. That is given by this graph here, which is L theta, your loss is on the y-axis, versus on the x-axis is going to be parameters, some parameters. This parameter here, theta star, at which point there is the least amount of loss, is essentially our optimal theta star. Now, the way we did it for logistic regression was we used something called gradient descent, right? We won't be using that because one of the reasons that least squares is very good based on the linear assumption of theta cap is that we have an analytical solution. Optimal, so this last sentence here, optimal theta cap can be found by solving its normal equation, which we'll do right now. Essentially, there is an analytical solution that gives us the best possible theta star in this situation. Again, gradient descent is also a methodology we can use, but it's not required because of the linear assumption that we have made. In logistic regression, we were not able to do that because we didn't have that linear assumption. Now we are able to have an analytical solution to this question. So this is where the math comes in. But if you're a grad student and you've taken ADSP, which is Advanced Digital Signal Processing, this is the first thing that is taught. Given a least square solution, what is the best result theta cap that you can get? So let's go through this. So 1 by n sigma n equals 1 to n, capital N, yi cap minus yi square. This is the least square loss that we had before. So whenever you have this kind of a square and the sigma, from a coding perspective, this is a for loop, right? But you can vectorize this entire statement by looking at it as a cosine distance, essentially, which is a dot b, a dot product is given by norm a, norm b, cos theta, right? So another way of writing a dot b is a transpose b, which is given by this thing here. So yi cap minus yi cap is the prediction, which is given by x of theta cap. So 1 by n x of theta cap minus y transpose multiplied by x of theta cap minus y. If you expand, if you just multiply x of theta cap with x of theta cap, you have x theta cap transpose x theta cap, and you get this expression. All you're doing is just multiplying x theta cap with this statement and then minus y with this brackets as well. You're getting this big statement here. Now, let me go back to this slide over here. Our goal is to find the optimal L or optimal theta cap. And we know that optimal theta cap exists when the loss is minimum. And that is when the gradient is going to be 0, right? So we want to create this dl by d theta and set it to 0. So that means that we're going to start by taking the derivative, dou L theta by dou theta. And we want to take the derivative of this expression, which is what we have over here. So this two lines are the mathematical equivalent for the derivatives. So we are taking theta cap transpose x transpose. I'm not sure if I explained this part, but this here, x of theta cap transpose is nothing but a b transpose is equal to b transpose a transpose. So this is just a simple linear algebra. This is how transposes work. The same thing has happened here as well. So your theta cap transpose x theta is, you're looking at x transpose x as basically a linear function, which you have taken it out. Now theta transpose x, if you look at it as a transpose b, which we have here in the dot product, it's essentially nothing more than norm A norm B cos theta. Since these two are exactly the same thing, theta transpose theta cap and theta transpose are the theta cap transpose and theta cap are the same thing. The cos between them is 0. So you can think of it as x transpose x theta cap square, and the differential of that is 2x transpose x theta cap, which is what you have over here. So that is the derivative of the first function. The second function, which is theta cap x transpose y, is more simpler because it's just a derivative with respect to theta cap, and which becomes 1. And what is left is your x transpose y. So for the third equation here, let me just name this 1. This is 2. This is 3. This is 4. 1. This is 2. 3 doesn't have it, but y transpose x theta cap. If I take a d by d theta of this, my answer is going to be y transpose x. Like, very simply put, it's just y transpose x, right? So what I have over here is the same thing back again. So I have x transpose x plus x transpose x theta cap equals 2x transpose x theta cap, which I can put back to this equation here, versus x transpose y. This becomes x transpose y, and 3 now becomes y transpose x, right? So y transpose x whole transpose is equal to x transpose y. It's the same expression. So I'm just going to add x transpose y, this plus this, to give 2x transpose y. Hopefully that part is clear. Actually, I'm not really sure how much this made sense. Maybe if this were in-person lecture, I would have run out of time by now. But since it's not, maybe I can take a couple of seconds to actually write this entire thing down. So let's start from the beginning again. You can probably, if you have understood this, just fast forward the next 2-3 minutes. I think it should be fine. So let's start with our expression that we had. So L of theta is 1 by n, sigma I equals 1 to capital N, yi minus y cap whole square. Right? This is the equation that we started off with. Now we know that y cap, which is prediction, is given by x theta cap. So this is something that we know. This is the linearity assumption. So anytime you see this, you know that you're dealing with a linear classifier. So another way of writing this is 1 by n x theta cap minus y, transpose x theta cap minus y. How do I? So this is essentially all I've done is now move to the second sentence here, which is I've taken this sigma, and instead of looking at it as a for loop, I'm now looking at it from a vectorized fashion. Now I can take L of theta equals 1 by n. Oops. Okay, something happened. I'm not really sure. So let me do that again. L of theta equals 1 by n. I'm just expanding the brackets over here. Another thing, important thing is AB transpose equals B transpose A transpose. So in this case, I have X theta cap transpose X theta cap minus Y transpose, minus Y transpose X theta cap minus cap transpose Y plus Y transpose Y. So each of these terms is the same thing associated with just multiplying within the brackets. So this is 1 by n x transpose theta, this using the equations that we have here, AB transpose, this is given by theta cap transpose x transpose x, theta cap minus y transpose x theta cap minus theta cap transpose x transpose y plus y transpose y. Hopefully that is the same set of equations we had y transpose x theta cap. The only difference between what is there in the slides is, in this case, they have a we have a transpose at this point, but again, it doesn't make a difference because AB transpose is the same as B transpose, A transpose. So with that, now this was L theta. Now we're going to set D of L theta. We're going to find D of L theta by D theta. So that is given by 1 by n, which is constant, just comes out. D by D theta of, we're going to take for each of these samples, theta cap transpose x theta cap minus 1 by n d by d theta of y cap x theta cap minus 1 by n d by d theta of theta cap transpose x transpose y plus d by d theta of y transpose y. Immediately you'll see that this is independent of theta, so that becomes 0. The first element derivative here, x transpose x, basically it's not dependent on theta by itself, but theta transpose theta, on the other hand, acts as this kind of a dot product, right, based on x transpose x. So theta transpose theta acts as a theta square. So what you have there is 1 by n, 2 x transpose x theta cap minus 1 by n. So if you differentiate it based on theta cap, you have y, I don't know, y transpose x, I believe that's not a cap, plus, oh, this is minus 1 by n. So you're expressing it with respect to theta here transpose, which will make it y transpose x plus 0, which is going to give you 1 by n, 2 x transpose x theta cap minus 2y transpose x, which hopefully should be what we have here as well. Perfect. So X transpose Y, or we have Y transpose X. I think it's the same thing here. I took it to Y transpose X and Y transpose X rather than X transpose Y. Again, AB transpose is the same as B transpose A transpose. So all the four elements, this is how you get the derivatives. Hopefully writing that was more clearer, but it's a very simple set of math that we have just progressed from one step to the other step. And once we get there, it's more straightforward, right? All we are doing now is setting d L theta by d theta to be 0. In other words, we are taking this and we are saying this is 0. So 2x transpose x theta minus 2x transpose y. And output you're going to get as theta cap is equal to x transpose x inverse multiplied by x transpose into y. Again, this should be very familiar as well. You've done the inverse. I think in homework, back in homework number 1, we had inverses. We never specified what kind of an inverse you need to use, but maybe you've used pseudo inverse and all the other things as well within the homework. So essentially, what you were doing before was solving for this generalized linear regression model and finding from a machine learning perspective, instead of optimizing for theta cap based on gradient descent, you were just finding an analytical solution for the normal equation and this coefficient vector, which is theta cap. And there's a very nice geometric representation as well to try to understand what this this normal equation x transpose x inverse x transpose y means. Essentially, what it is telling us is that the minimum distance that can exist between this kind of a hyperplane that is formed by our function f and a data point which has a value of y is going to be this orthogonal function, right? Every single point or every single, the f function is defining this kind of a p+1 dimensional linear subspace. And this subspace is spanned by all x or all data points that we have access to. The dimensions of a particular data point is going to span this particular subspace. And given any kind of an estimate, y cap, it lies in the subspace so that it's closest to y. This orthogonality, it exists. It's a little bit more math is required to move from trying to understand this to try to understand this. And that is given by this idea of projection matrices, orthogonal projection. If you're interested, you can go through and study more about what orthogonal projection means. Projection matrices mean this, in fact, is a projection matrix. I think I have a couple of references within the course content. If not, I think I can add a few references. But there's a very nice way of trying to understand this kind of a geometric interpretation for generalized linear regression model, where given any kind of data point, we get a subspace that is spanned by all data points, and the minimum distance between the prediction and the true value is an orthogonal projection on that subspace. So that is essentially what we did with this idea of generalized linear regression model for the particular cost function of least squares, based on the fact that we made an assumption about linearity. Another nice feature about having this kind of an analytical solution is the idea that we can kind of compress features. Maybe some features are important for making our decision, for finding that relationship, but maybe there are some features that are redundant. And you can use these kind of analytical solutions in order to make those decisions. For instance, x transpose x is it's a very nice vector, because in certain cases, this x transpose x can be invertible. And even if it is not, then we can use this singular value decomposition in order to see the rank of the matrix and to see which of the eigenvalues within the x transpose x is 0. And if that is 0, then that means that the column vectors within U and the row vectors within V are not really contributing to the x transpose x, are not contributing to that subspace. So we can remove those columns, right? So that means that there are some features which are not really helping us in making this, in creating this kind of a hyperplane and a subspace. We'll revisit this concept again in something called dimensionality reduction when we do clustering. But just remember this idea of how we can use singular value decomposition in order to remove certain features from our data, because those data points are very there's a lot more redundant features within our data than we would like. All right, so this is the last part for this lecture, which is multi-output regression. So we, till this point, right, we just looked at y as a single number. It's a 4.2 or a 4.5, or that life satisfaction index where it was going from, if I remember correctly, somewhere between 4 to 12. But it need not be a single number. It could be vector as well as x. So in this case, I have x from 1 to xp. I can also have y as y from 1 to k values. And this is what we would call a multi-output regression. We can make the same assumptions here as well. Y equals x theta, where maybe a single number y1 of 2 is, or y of 2 is always dependent in a linear fashion, with all the other x's and thetas. That might be the case, might not be the case, right? But if we make that assumption, then we have all the analysis that we have done till now is going to work here as well. Hence, it's going to be a multi-output regression. I think we have used the term kth function. So yeah, maybe kth function here is what we have used in the slide. So this setup, this framework is called multi-output regression, where the vector y itself is not a number, but it could be this vector. Now, we won't go deep into multi-output regression, but in more realistic real-world scenarios, this is essentially what is always used. We never have this kind of a very simple number as our output. Generally, it's a lot more of a vector than otherwise. Again, we won't go deep into the multi-output regression in this, at least in this lecture. So that brings us to the end of lecture number 7. We looked at a couple of things, the performance metrics and linear regression. I'll try to upload this now, and you should have access to it. And I'll also make an announcement that there is not going to be a in-person lecture tomorrow. Hope everything is fine. The video has come out fine, and you should be able to see it tomorrow. Thank you.